Hi guys, up to now we have been dealing with the concepts of limit and continuity with the function. So, I told you how do we define a limit. Basically, limit is limiting x tending to a fx is equal to a finite value. Now, I told you for the limit to exist, there are two limits defined. One is called as left hand limit, other is called as right hand limit. And if both are equal, that is left hand limit is x tending to a minus, it should be equal to the right hand limit x tending to a plus fx. Then the limit will exist. This can also be expressed as limiting h tending to 0 f of a minus h is equal to limiting h tending to 0 f of a plus h. Okay, that is a point just after the a and a point just before the a. Then we said if both these limits are equal and it is equal to the function value fa, then basically it implies continuity of a function. Okay, and I also told you whenever there is an indeterminate form, then we use L'Hopital rule to derive the limit. In that what we do is limiting x tending to 0 fx gx is equal to limiting, or let us say x tending to a, limiting x tending to a f dash x by g dash x, in case you have the form 0 by 0 or infinity by infinity. I also told you about other indeterminate forms like 1 raised to the power infinity, 0 raised to the power infinity, 0 into infinity, infinity into 0. Okay, all those forms must be first converted into a form of 0 by 0 or infinity by infinity. Then we can apply L'Hopital's rule in order to find the limit. In this lecture, we will talk about another important aspect that is related to a function, that is called as differentiability. Now, differentiability means if a function can be differentiated. Differentiated means its derivative exists. Now, what is derivative? Basically, derivative represents slope of a tangent at a point. Okay. How is it that? Now, if I give you a line, suppose this is the point A, this is the point B, and this value is FA, and this value is FB. Then how you determine the slope? We determine the slope like this, delta y by delta x. So, slope will actually be equal to delta y upon delta x, that is equal to FB minus FA over delta x is actually B minus A. Now, if we take a function like this and I draw a line between the 2 points, then its slope will be same, that is delta y by delta x. Now, if you bring these 2 points close enough, then basically this line will become a tangent. That is, if B and A are close to each other, then the secant or the line joining the 2 points will actually become a tangent. So, if you want to derive the slope of the tangent, then B and A must be close together. For that purpose, what I will do is I will define B as A plus H, where H will tend to 0. That is, the 2 points are very close. So, this slope will become equal to limiting H tending to 0 f of A plus H minus f of A divided by H. B minus A will be equal to H. That is known as your derivative, and it is actually known as right hand derivative because the point that you are taking is existing to the right of A. This will be represented by f dash A. Dash represents the first derivative. So, if you are taking derivative twice, you will denote by f double dash A. Triple times derivative, it will be f triple dash A. Something like that. Okay. Now, what is the condition that a function should be differentiable? The condition is that we will define two derivatives, one called as right hand derivative, other called as left hand. Because if you want to derive the slope, you need 2 points. The 2 points can be the point A and the point just to the right of A. the point A and the point just to the left of A. You can use any of these two combinations in order to derive the slope. Now if you use the point to the right of A, it is known as right hand derivative, which is given as limiting h tending to 0 f of A plus h minus f of A by h. Then similarly, left hand derivative will be given as limiting h tending to 0 f of A minus f of A minus h by h. Okay. If both these derivatives are equal, then the function will set to be differentiable. Okay. So these must be equal as well as these must be finite. They both are equal to f dash A. Is it fine? So a function, now we have two cases, whether the function is differentiable in the open interval or the closed interval. I already explained to you the meaning of open and closed interval. So if we talk about closed interval, then it will be like A to B. Now if you see point A, since we haven't included any point before A, that means we cannot calculate the left hand derivative at A. Because to calculate left hand derivative, you need a point just before the A, but my interval begins only at A. Similarly, to calculate right hand derivative at B, we will need a point that lies just after B. And as you can see, the interval ends at B, there can be no point just beyond B. So, to define differentiability, we will say that right hand derivative is equal to left hand derivative for all x belonging to open interval AB. But at point A, we cannot calculate left hand derivative. So we will say at x equal to A, the right hand derivative exists. And at x equal to B, left hand derivative exists. We cannot talk about right hand derivative at B and left hand derivative at A. Is it fine? Now, similarly, when you talk about open interval, then actually A and B are excluded from this interval. So no need to care about A and B. We will just say the right hand derivative must be equal to left hand derivative for all x belonging to A and B. Is it fine? Because all the points that I am considering are lying between A, B, so we can calculate both the derivatives. But since A and B are the end points of the interval, you cannot take any point before A or after B. So that is the problem with the closed interval, and it is not a problem with the open interval. Now, how differentiability and continuity are related? So this statement you must always remember. Whichever function is differentiable, it by default implies continuity. Okay. But continuity does not necessarily imply differentiability. Okay. It is not necessary if any continuous function will be differentiable. How so? So let me show you an example. So suppose I take a triangular function like this. Now as you can see, this is perfectly continuous. There is no sudden change anywhere. But now let us check the slope at 0. If you go just before 0, this will be my slope. That is tan theta. If you go just above 0, the slope will be negative. Here the slope is positive. Is it fine? That means the slope suddenly changes before 0 and after 0. And since slope is represented by derivative, the left hand derivative is positive, whereas the right hand derivative is negative. So here the left hand derivative is not equal to right hand derivative. Hence it is not differentiable. Is it fine? Though it is perfectly continuous. So remember, continuity does not imply differentiability, but if a function is differentiable, it is definitely continuous. Now let me show you an example. Here we are given a function fx is equal to x mod x. We need to check its continuity and differentiability. Now I have already told you mod x is equal to x for x greater than 0 and mod x is equal to minus x for x less than 0. Due to which what happens to the function fx? It will be x into x, that is x square, for x greater than 0, x into minus x, that is minus x square, for x less than 0, and it will be 0 for x equal to 0. Now let us first talk about continuity. Now for continuity I need to check the left hand limit and the right hand limit. So I will say limiting x tending to 0 minus fx. For less than 0 we have the function minus x square. So it will be limiting x tending to 0 minus x square, that will be 0. What about right hand limit? It will be limiting x tending to 0 plus fx. For any value greater than 0 we have the function x square, that is limiting x tending to 0 plus x square, which is also 0. Now as you can see, the left hand and the right hand limits are equal, that means limit exists. And these limits are equal to the function value at 0. So this is definitely continuous. Now let us check for differentiability. Now when we are talking of differentiability, we will check the right hand and the left hand derivative. So if we write down f dash x, it will be 2x for x greater than 0. Because for x greater than 0 function is x square, so its derivative will be 2x. And its derivative will be minus 2x for x less than 0. And it will be, we do not know the derivative at 0. Is it fine? Now if you see the right hand derivative, it will be limiting x tending to 0 plus f dash x, which will be limiting x tending to 0 2x, which comes out to be 0. What about left hand derivative? Limiting x tending to 0 minus f dash x, that is limiting x tending to 0 minus 2x, which comes out to be 0. So the right hand and the left hand derivatives are equal, and hence we will say the function is differentiable. Is it fine? Now if you wanted to check directly, then we can also draw the graph of this function. As we know, the function is equal to x square when x is greater than 0, and it is minus x square for x less than 0. The graph will be like this. Okay. Now as you can see, the graph is perfectly smooth at x equal to 0. There is no sudden change or there is no sharp turn. So it is continuous and differentiable. Okay. A function is not differentiable whenever it takes a sudden change, like, or there is a sharp turn like this. Now as you can see, it had turned sharply from one point to the another, then it will not be differentiable. Moving on to the next concept. Next we come to the concept called as mean value theorem. So in mean value theorem, we first of all face Rolle's theorem. What does Rolle's theorem states that? It states that first condition, fx is continuous in closed interval a to b. Then fx is differentiable in open interval a to b. Then the next condition is fa equal to fb. So remember three conditions for Rolle's theorem: 1, 2 and 3. That is, fx is continuous in the closed interval, it is differentiable in the open interval, and the value at both the endpoints is same. So if these three conditions are satisfied, it says there exists a point C belonging to A and B such that f dash C is equal to 0. Okay, this symbol represents there exists. Okay, so in between A and B, definitely there will be a third point C at which the derivative will go to 0. Why I am saying this is, suppose this is my function. Now if you see, if we take 2 points where the values of the function are equal, then there will be a third point where the derivative is 0. Derivative represents the slope, and if the slope is 0, it means it is a horizontal tangent. So that is what my Rolle's theorem states. Is it fine? So the necessary condition you should always remember: continuity in closed interval, differentiability in open interval, and values equal at both the end points. But the thing is that it does not necessarily imply, or the converse of Rolle's theorem is not true. What does that mean? If I tell you that there is a point at which the derivative is 0 in the interval, it does not mean the value at both the endpoints will be same. How? Suppose I take a function like this. Okay, so here derivative is 0. Let me choose this interval, that is a and b. Now if you see, a has the value f of a, b has the value f of b. As you can say, fa is not equal to fb, but still there is a certain point, let us say x, where the derivative is 0, or you can say the tangent is parallel to x-axis. Because the derivative indicates the slope of the tangent, 0 slope indicates it is parallel to x-axis. So let me show you how do we apply this theorem. So it is asking me to find the mean value c for the function fx equal to this. Now if you calculate a is actually the lower part of the interval, that is pi by 4. So what is fa? E raised to power pi by 4 sin pi by 4 minus cos pi by 4, which will come out to be 0. What about fb? fb will be e raised to power 5 pi by 4 sin 5 pi by 4 minus cos 5 pi by 4. At 5 pi by 4, sin and cos both have the value minus 1 by root 2, so their difference is 0. So as I can see, fa is equal to fb. And since the function consists of exponential and the sine cosine function, it is definitely continuous and differentiable. So there must be a third point c such that f dash c is 0. So if you take the derivative of this function, it will be e raised to power x sin x minus cos x plus e raised to power x cos x plus sin x. So it will be 2 e raised to power x sin x. So if there is a point c at which the derivative is 0, what I can say? 2 e raised to the power c sin c is 0. Due to which c can have all the possible values, that is n pi. That is, it can be plus minus pi, plus minus 2 pi, plus minus 3 pi, as well as 0. But we have the condition that c will lie between these two points. And out of all these points, only c equal to pi lies between pi by 4 and 5 pi by 4. So that is my answer. Okay. So you may get multiple points, but you always have to check at what point is it lying between the upper and the lower limit. Now let us move on to a more general mean value theorem, that is the Lagrange mean value theorem. The necessary condition is still same. fx must be continuous in the closed interval and it must be differentiable in the open interval. But we remove the third condition, that the values at both the endpoints is same. So it changes the condition and it states that there exists a point c belonging to a to b such that f dash c is equal to fb minus fa over b minus a. Now what does that mean? If I give you a function like that, now suppose this is a, this is b, then you draw a line joining a and b and calculate its slope. The slope will be this much. So there will be a point c between a and b at which you will get the same slope. So this point will be c. Is it fine? At which the tangent is actually parallel to the secant or the line joining the points a and b. So that is your Lagrange's mean value theorem. Now you can directly see here, if fa is equal to fb, then f dash c will come out to be 0, which indicates that Rolle's theorem is a special case of Lagrange's mean value theorem. Is it fine? So that is why it is more general to apply the Lagrange mean value theorem, though the converse of Lagrange may also not be true. Like I told you in the Rolle's theorem, the converse may or may not be true. Similarly here, the converse may or may not be true. But the thing is, the applications of Lagrange's theorem are very interesting. The first application is increasing and the decreasing function. Now if I tell you, for all c belonging between a and b, f dash c is greater than 0, then what does that indicate? fb is greater than fa according to LMVT, that is Lagrange's mean value theorem, because f dash c is equal to fb minus fa over b minus a. Okay, it means the function value at a higher point is higher as compared to a lower value, which indicates an increasing function. Okay, because an increasing function will increase with the increase in x. So if you take a higher value of the input, you will get a higher value of the output. Since b is greater than a, the output at b, that is fb, is definitely greater than fa. Now there are two cases even in the increasing function. The special case is known as strictly increasing function. Okay, what is meant by strictly increasing? That f dash x is greater than 0 for all x belonging to a interval, whereas just increasing means f dash x is greater than or equal to 0. Okay, so strictly increasing means it must always be rising and even it cannot saturate. But strictly increasing means it can saturate. That is, if I give you a curve like this, then it is actually increasing function. But if I give you a curve like this, then it is strictly increasing. Similarly, the converse if we talk about, that is, if I give you the derivative is derivative is less than 0, what does that mean? If derivative f dash c is less than 0 for all c belonging to a to b, then that means fb is less than fa. That is, as you move forward from a to b, the value of the function reduces, which means it is a decreasing function. So if I give you a function like this, and this is my a, at which the value is f of a, and this is b, at which the value is f of b. As you can see, though b is greater than a, but fb is less than f of a. So it is a decreasing function. Now again in decreasing we have two categories. One is known as decreasing. In that case, f dash x can be less than or equal to 0. And the next we have strictly decreasing, in which f dash x should be strictly less than 0. Like if you see this function which continuously decays, this is strictly decreasing. But if I give you one function like this, then it is actually decreasing, because after a certain time its slope becomes 0, that is, the derivative goes to 0. Is it fine? The last case is when f dash c is equal to 0. If f dash c is equal to 0, then that means the function value is same at both the endpoints. In that case, it is a constant function. Because I am talking about at each point, that is for all x, if f dash x is 0, which means the slope is 0 for the curve at all points. If slope is 0, then the function remains at a constant value. So that will be my constant function. Okay. So this is all the application of LMVT. That is, if derivative is strictly greater than 0, it is a strictly increasing function. If it is just greater than or equal to 0, it is increasing function. And If it is equal to 0 at all points, then it is a constant function. The next mean value theorem that we look at is called as Cauchy's mean value theorem. Now it takes into account two functions which are defined, that is fx and gx are defined in a to b. Now again we have same condition, fx as well as gx is continuous in a to b. Then fx, gx are differentiable in a to b. Then we will say g dash x is not equal to 0 for all x belonging to ab. Shortly I will reveal you the reason for this assumption. Then it says that there exists a point C belonging to AB such that f dash C over g dash C is equal to fb minus fa over gb minus ga. Is it fine? Now you will think that this mean value theorem does not convey any additional information as compared to LMVT. Because if you consider two functions in LMVT and apply LMVT to both and then take the ratio, you will get the same result. But the loophole in that derivation is that you are assuming that the same point C will be applicable for both the functions. It may so happen that the value of C is 2 for first function and it is 3 for the second function. So Cauchy's mean value theorem gives me an additional information that f dash and the g dash are taken at exactly the same point. Now as you can see, g dash is appearing in the denominator. It is pretty necessary for me to have a condition that this must be non-zero, otherwise their ratio will become infinite. That means g must be either a increasing or a decreasing function, that is strictly increasing or strictly decreasing. In a to b, its derivative can never be 0 in such a interval. So let me summarize what we have covered in this lecture. I first told you about the concept of derivative. What is derivative? And I told you the meaning of differentiability. Okay. The condition that we saw for differentiability was right hand derivative is equal to left hand derivative. Then we moved on to the mean value theorem, in which we first saw Rolle's theorem. In Rolle's theorem I told you f dash c is equal to 0, or there exists a c belonging to AB such that f dash c is 0 if fa equal to fb, where f is a function continuous in closed interval a to b and differentiable in the open interval a to b. Then we saw Lagrange's mean value theorem, which said that f dash c is equal to fb minus fa over b minus a. Here all the conditions remained same except for the fact that fb equal to fa. Then we saw Cauchy's mean value theorem, which took into account two functions and said that f dash c by g dash c is equal to fb minus fa over gb minus ga. So that is what we have covered in this lecture. In the next lecture, we will see some problems based on the concepts covered in this lecture.